Igneous rock formation. So magma is molten rock that's below Earth's surface, while lava is actually magma that flows out onto Earth's surface. So the big difference is where it's located. So technically, this is lava. It's actually out on the Earth's surface, so that is lava. Magma, again, is below Earth's surface. Now, igneous rocks form when lava or magma cools and crystallizes. You can literally watch them form if you visit an active volcano. So if you visit an active volcano and there are lava flows, like in Hawaii or something like that, you can literally watch igneous rocks being formed. So a quick review of the layers of the Earth. So we start with the outer layer. You got the crust, okay? Then we've got the mantle, which is just below that, and that's where a lot of our magma is actually at. It's actually in the mantle and comes up into the crust. Then you got the outer core and the inner core, okay? So that's just our basic anatomy of the Earth here, the layers of the Earth. So melting temperatures. So in the lab, rocks melt at 800 degrees Celsius to 1200 degrees Celsius. In nature, these temperatures are present in the upper mantle and lower crust. So you've got the lower part of the crust and the upper part of the mantle, which would be basically right in this area, right in here. Okay, so that's where we start to get those temperatures. So this thermal energy likely comes from two sources. So first off, it's leftover energy from Earth's molten formation. So as the Earth formed, a lot of meteors and planetesimals and larger bodies of rock kind of came together, and the friction from that heated the rocks up and caused them to melt. And then that energy has been trapped in the interior of the Earth because the crust kind of acts as an insulation layer, or a layer of insulation that kind of traps that heat. You also have heat generated from the decay of radioactive elements. So you have different radioactive elements that are in the crust and in the mantle and in the core, and as those elements decay, they are actually releasing a lot of heat. So the composition of magma. So the type of igneous rock that forms depends on the composition of the magma. So magma is often a slushy mix of molten rock, dissolved gases, and mineral crystals. Some common elements in magma are the same major elements in Earth's crust. So oxygen, silicon, aluminum, iron, magnesium, calcium, potassium, and sodium. So those are our main elements that are in the rocks in Earth's crust. Those are also a lot of the main elements in our magma. Silica is the most abundant compound and has the greatest effect on magma characteristics. And silica is basically quartz. We talked about minerals. So SiO2 is basically silica. So classification of magma. So magma is classified as basaltic, andesitic, or rhyolitic based on the amount of silica that it contains. Silica content affects melting temperature and viscosity. And viscosity basically means a resistance to flow. Sometimes you might think about how thick a liquid is. So cold syrup, like cold maple syrup or something like that, has a higher viscosity than water. Actually, even just room temperature maple syrup has a higher viscosity than water. Honey has a very high viscosity. Okay. More silica means higher viscosity. Okay. More silica also means lower melting temperature. So if we increase the amount of silica, we decrease the melting temperature. So if you've ever seen molten glass, that's kind of what the consistency of silica is, or the viscosity of silica. So our three types, again, we have basaltic. Okay. This has our lowest silica content, 45 to 52%. Common in the Hawaiian Islands. We have andesitic lava, which is somewhere, or andesitic magma, which is somewhere in the middle. So 52 to 66% silica content. Cascade Mountains out west, out in the western part of the U.S., and the Andes Mountains in South America. Rhyolitic lava is any lava that is more than 66% silica, and Yellowstone National Park is an example for that. So lava versus magma composition. So when magma reaches the surface, it is free of the pressure of the overlying rock. So the rock on top of it provides a lot of pressure to keep gases and stuff in. So once you remove that pressure, this allows those gases to escape to the atmosphere. Now, the pressure keeps the gases dissolved in the magma, very similar to a lid on a soda bottle. So the lid on the soda bottle traps carbon dioxide gas in the soda bottle and keeps it dissolved in the soda. When you take that lid off, that gas can start to bubble out. That's why it starts to fizz when you take the lid off of it. And it's also why it tends to go flat if you leave it sitting there for a while, because all of the CO2 gas kind of bubbles out. So this means that lava has a slightly different composition than the magma that it came from. This is like flat soda versus fizzy soda. It's fizzy because it's got carbon dioxide gas dissolved in it. Okay. Once all that carbon dioxide gas bubbles off, then you've got flat soda with less carbon dioxide gas in it, or no carbon dioxide gas in it. Okay. And that's allowed to be released because you've released the pressure that was holding it in there. Now, magma formation. So magma can be formed either by melting of Earth's crust or melting in the mantle. So you can melt two different things here. So you can melt the crust itself, or you can have the mantle melting. Now, there are four main factors involved in magma formation. So you got temperature, okay? You've got pressure, you've got water content of the rocks, and then you've got mineral content of the crust or mantle being melted, okay? So, and also technically, so this is magma formation. Technically, this is lava again, because it's on the Earth's surface. It's not magma. It's hard to get a picture of magma because it's underground. So, but again, we have these four main factors we're going to talk about individually here. So temperature of magma formation. So temperature increases with depth in Earth's crust. As you go deeper into the crust, the temperature increases. I mean, this is known as the geothermal gradient. Now, the average gradient in the crust is about 25 degrees Celsius per kilometer. So for every kilometer you dig down, the temperature increases by 25 degrees Celsius. Once you get through the crust and into the mantle, we don't know for sure, but we think it's 1 degree Celsius per kilometer in the mantle. Now, oil well drillers and miners have experienced this firsthand. So some drill bits experience temperatures in excess of 200 degrees Celsius when drilling deep wells. So again, so here's our depth into the earth. This is actually all the way through the crust, mantle, inner and outer core. And then we're going to have our temperature going up the y-axis here. So this is just kind of showing that as you go deeper into the earth, the temperature does increase. It increases pretty rapidly at first. And then as you get closer to the core, it starts to kind of even out a little bit and get flatter as far as our temperature curve here goes. So when you get closer to the core, it kind of maintains one stable sort of temperature here. Now, pressure and magma formation. So pressure increases with depth. We kind of know that intuitively. Think about water. Water pressure increases with depth. Well, if you go deeper into the earth and there's more rock over top of you, that pressure is going to increase as well. So more overlying rock pressing down on you increases that pressure. Now, increasing pressure increases our melting point, because if we think about a liquid here, if you have more pressure pushing in on that, it's going to push all your particles back together. So when something melts, okay, so it's solid here. So if we think about this being solid, so with this being solid, all these particles are stuck together. Well, to get it to melt, you have to get enough energy in these particles that they can all spread out and start moving around each other. If you are squeezing in on this and applying a lot of pressure, it makes it harder for them to actually start to move around each other. So it increases your melting point. So rocks that melt at 1100 degrees Celsius in the laboratory melt at 1400 degrees Celsius at a depth of about 100 kilometers. So the deeper you go into Earth's crust, the higher the melting point. Now, what can happen is due to density differences, some of this hot rock that's deeper in the crust can actually start to move up. So as it moves up, this pressure decreases, and that will allow the melting point to start dropping to the point that it will actually melt. But think of higher pressure as squeezing these particles together, okay? And this is kind of what's happening here. So you have increasing temperature going this way. Okay, so our increasing temperature going across here. We have increasing pressure and depth going this way. So if we have a bit of rock here, okay, this is called decompression melting. So you have this bit of rock here. Due to temperature and density differences, this will want to try to rise up. If at that same temperature, if it stays the same temperature and it gets to a shallower depth, well, it may get to a point where it's going to partially melt because that block of rock has moved up and got to a point where the pressure is lower, so it's able to melt at that point. It's called decompression melting because you're lowering the pressure, and that allows something to start to melt. Water content in magma formation. So rocks and minerals often contain small amounts of water. Water content changes the melting point. Basically, if we increase the water content, we decrease the melting point. So increasing our water content decreases the melting point. Okay, so here we have increasing temperature again. We have increasing depth and pressure, same thing basically. So our dry mantle rock is actually going to melt out here at these higher temperatures. Okay, if you add water to that rock, it basically shifts the curve over to here. So basically what that means is, since we shifted this curve over to the left, basically means it's going to melt at a lower temperature. So it's going to melt maybe at this temperature instead of having to get up to this temperature for a given depth, right? So maybe this is the depth you're looking at here. Well, if it's got water in it, it's going to melt at this point. If it's dry, it's going to melt over at this point. So if it has water in it, it's going to melt here. If it's drier, it's going to melt over here. Okay, so again, the more water you have in that rock, the more likely it's going to melt. Because the water kind of acts as sort of like a lubricant to kind of allow those particles to start moving around each other. Mineral content and magma formation. So different minerals have different melting points. So for example, basalt is composed of olivine, calcium feldspar, pyroxene, etc., giving it higher melting point than granite, which is made of quartz and potassium feldspar. So in other words, olivine and calcium feldspar and pyroxene have just higher melting points. These minerals in pure form have a higher melting point than quartz and potassium feldspar. So since basalt has more of these minerals, it's going to have a higher melting point. The granite has lower melting point minerals, so it's going to have a lower melting point. So granite has a lower melting point because it contains more water as well, and minerals that melt at lower temperatures. In general, rocks rich in iron and magnesium melt at higher temperatures than rocks that contain higher levels of silicon, okay, or silica. So higher levels of silicon and silica basically is going to have a lower melting point. Rocks that have a lot of iron and magnesium, usually darker colored rocks, tend to have higher temperatures. So partial melting. So if you freeze candle wax with water in an ice tray, you'll have an ice cube that has bits of wax in it, all right? So if that's left sitting on the counter, what's going to happen? The ice is going to melt because the ice has a melting point of 32 degrees Fahrenheit or 0 degrees Celsius. Well, room temperature is about 20 degrees Celsius. So the room temperature is above the melting point of the ice, so the ice is going to melt. But the wax has a much higher melting point, so the wax is not going to melt just sitting on the counter. Okay. Rocks melt the same way because they're made of different minerals, and those different minerals have different melting points. So this results in magma that's a slushy mix of crystals and molten rock, because some of those crystals have higher melting points and the molten rock is not hot enough to melt those. Okay. So for example, here we have solid rock, which has biotite, and plagioclase feldspar, potassium feldspar, and quartz and hornblende. Okay. So as you start to heat that rock up, different things are going to melt. Like the first thing that's going to melt is going to be our quartz. This has the lowest melting point. Okay. Then the next thing is going to be the plagioclase feldspar. It has the next lowest melting point, so it's going to melt. Okay, and then what that leaves you with then is your potassium feldspar, your biotite still in here, your hornblende still in here because it hasn't got hot enough to melt those three yet. But then you also have this molten rock. Well, that molten rock is actually just your quartz and your plagioclase feldspar that have melted and gone into this molten rock. And we call that partial melting. And it's the process whereby some minerals melt at relatively low temperatures while other minerals remain solid. And then partial melting of magma composition. So as groups of minerals melt, different elements are added to the magma. And this changes the composition of the magma because you're adding different elements to the magma. It also takes out certain crystals that are in the magma. So it may be a slushy mix of certain crystals, and then some of those crystals melt, and then that gets added to the magma. Those elements that make up those crystals get added to the magma, etc. So the magma will have a different composition from the parent rock if temperatures are not high enough to melt the entire rock. Okay, so if you can't melt the entire rock, then the magma is not going to have the same composition as that parent rock. So this results in different types of igneous rocks forming. So what we have here is at lower temperatures, say 600 degrees Celsius is about our melting point for silica. About 1200 degrees Celsius, everything melts. So lower temperatures here, we have no melting. Then we start to have our silica melt first. So we have a lot of silica in the magma if it's at about 600-700 degrees Celsius. As that temperature increases, more and more minerals melt. So the relative proportion of silica starts to go down because most all your silica is going to melt 600 to 700 degrees Celsius. So it's really high in silica at that point. But then as it heats up, more minerals melt. So the relative silica content of the magma goes down because you can't really add more silica to it because it's already all melted. So then you start adding in like your iron and magnesium and other elements like that. So the relative proportion of that silica goes down